When you stand at the edge of a lake and see a few ducks or geese peaceful on the surface, it's difficult to realize if you were to shrink down a million times smaller and venture below, you'd find a bustling, invisible world teeming with life. This is the world of phytoplankton, microscopic organisms that float in the sunlit upper layers, forming the very foundation of the lake's existence. Like plants on land, these tiny life forms are part of the vegetable kingdom. They harness the sun's energy through photosynthesis to create their own food and fuel their growth. They are the base of the food web, providing sustenance for the zooplankton, the microscopic animals of the lake, which in turn feed small fish and so on up the chain. This community of phytoplankton is incredibly diverse. It includes groups with names like diatoms, green algae, cryptophytes, and chrysophytes. For the most part, they are the silent, beneficial gardeners of the aquatic world. But there is another member of this community that behaves very differently: cyanobacteria. And understanding the difference between true beneficial algae and cyanobacteria is critical, because it can be the difference between a healthy, thriving lake and one that is in serious trouble. So, let's start with the good guys. What exactly are these beneficial algae? This category includes several key groups. You have the diatoms, which are like the nutrient-packed superfoods of the lake. Then there are the green algae, known for being fast-growing and rich in energy, basically the high-carb energy source for the ecosystem. And you have other diverse groups like chrysophytes, cryptophytes, and dinoflagellates, which help create stable, resilient populations. Together, these groups are the engine of a healthy lake.
Through photosynthesis, they produce the dissolved oxygen that fish and other organisms need to breathe. They are the primary food source for zooplankton, ensuring the next level of the food web is well-fed and robust. This, in turn, supports healthy fish populations. They are a sign of balance, thriving in water with healthy levels of nutrients and oxygen. You can't have a functioning lake without them. They are, quite simply, essential. But then there are the cyanobacteria, and this is where the story gets complicated, because cyanobacteria are not true algae at all. They're actually bacteria that evolved the remarkable ability to photosynthesize. Because their fundamental biology is different, they play by a completely different set of rules. They often grow at an explosive rate, far faster than beneficial algae. Many species can produce potent toxins, which can be harmful to fish, wildlife, pets, and even humans. And they have a unique tolerance for conditions that would stress or kill beneficial algae. They thrive in warm, stagnant, nutrient-rich water. Under these eutrophic conditions, they don't just survive, they outcompete and dominate everyone else. Let's break down that comparison. On one side, you have beneficial algae, which are true algae. On the other, cyanobacteria, which are photosynthetic bacteria. Beneficial algae exhibit moderate, stable growth. Cyanobacteria can be explosive, forming the dense blooms we see on the surface. For the food web, beneficial algae are a high-value meal. Cyanobacteria, however, offer low to no food value, and worse, can be toxic. Beneficial algae are indicators of a balanced, healthy lake. Cyanobacteria are often a sign of a stressed system, one with too many nutrients and not enough oxygen. In short, one supports the food web while the other fundamentally disrupts it. The balance between these two groups often determines whether a lake remains a stable, healthy ecosystem or begins a downward spiral. So what allows cyanobacteria to take over? They gain this powerful competitive advantage under a specific set of conditions increasingly found in lakes stressed by pollution and climate change. First, they need high levels of nutrients, especially phosphorus and nitrogen, which often come from agricultural or urban runoff. Second, they love warm water.
They do their best work in the summer heat. Third, they prefer calm, stratified lakes where the water isn't mixing much. This allows them to use their buoyancy to rise to the surface and bloom. And finally, they benefit from low oxygen in the deep water. When the sediment at the bottom of the lake becomes hypoxic, or oxygen-starved, it releases a burst of nutrients, providing even more fuel for cyanobacteria to dive down and feast upon. These conditions weaken the beneficial algae and create the perfect storm for a cyanobacterial takeover. And they have a secret weapon that no true algae possesses: gas vesicles. These are tiny, gas-filled compartments inside their cells that act like microscopic buoyancy compensators. Using these vesicles, they can move up and down through the water column at will. They can descend to the dark, nutrient-rich bottom layers to load up on phosphorus released from the sediment. Then they can inflate their vesicles and rise back up to the sunlit surface to photosynthesize, forming thick blooms that shade out all their competitors below. It's an incredible advantage, allowing them to access the best of both worlds, nutrients from the bottom and sunlight from the top. This is why the composition of the phytoplankton community matters so profoundly. A healthy lake has a diverse portfolio of phytoplankton. This diversity ensures a stable flow of energy through the food web. It supports strong zooplankton populations by offering a varied and nutritious diet. It promotes balanced nutrient use, so no single group can monopolize resources. The result is clearer water and a much lower risk of sudden harmful blooms. But when that diversity collapses and cyanobacteria dominate, a cascade of problems begins. Zooplankton lose their high-quality food source, and their populations shrink. This means less food for small fish, and fish recruitment declines. Water clarity drops dramatically as the dense blooms block sunlight. Toxins may appear in the water, posing a risk to the entire ecosystem, and blooms become more frequent and more severe. So when you see that green scum on the surface, what you're really seeing is a symptom of a much deeper issue. The entire lake's food web is shifting toward instability. Because of this, tracking the composition of phytoplankton over time is one of the most powerful ways to understand where a lake is heading. Think of it as reading the lake's vital signs. A measured shift back toward a diverse community of beneficial algae is a sign of improving conditions, a lake in recovery. But a steady shift toward cyanobacteria dominance signals increasing stress and a system on the verge of collapse. This single indicator, the ratio of good algae to cyanobacteria, tells us a story about nutrient loading, oxygen levels, and the overall strength and direction of the ecosystem. In the end, it comes down to a few key ideas. First, not all algae are equal. The microscopic world of a lake is a complex community with different players. Second, beneficial algae are the cornerstone of that community, supporting the entire food web. Third, cyanobacteria are photosynthetic bacteria, not true algae, and they thrive under stressed conditions that they, in turn, make worse. The balance between these groups truly determines the water quality and health of the lake. The story of a lake's future, whether it remains a vibrant ecosystem or slips into decline, is written in these microscopic communities. And by learning to read that story, we learn how to protect it.
Understanding this microscopic distinction is vital for public safety. In Lesson 5, Toxic Scum, we will look at what happens when these cyanobacteria take over completely, creating the toxic surface scums that threaten pets, wildlife, and humans. To go to the next lesson, use the link below. And don't forget to subscribe, like, and share.